Good afternoon and welcome to the penultimate of the 2019 Digital Classicist London seminar series. Now before we start, next week, the last week of this summer's series, we have Kelly McClinton from Bloomington talking to us about the application of photogrammetric 3D modeling to domestic space. Today, however, we have the pleasure of welcoming to us Ghigo, who is a PhD candidate from both La Sapienza and University of Hamburg, and she's going to dazzle us with archeometric analysis of writing inks from Coptic manuscripts.
Thank you. All right, so
did you screen share?
Maybe I didn't. Sorry.
Just double check. But
all right.
Yeah.
Okay. Now,
There you go.
perfect. All right. Okay. So, good afternoon, everyone. I'm really happy to be here. I would like to thank Valeria for the suggestion of coming here to this event today. So before starting, I would like to do a couple of remarks on what I'm going to talk about. All right. So first of all, I have to say that although at the beginning I was dealing only with Coptic inks, with Coptic manuscripts, because of the difficulty in actually finding manuscripts that were securely dated in the Coptic period, we decided to extend the investigation to generally late antique Egyptian manuscript, including also manuscript, for example, in Latin or Greek, any other language than Coptic. And then I would like to talk for a while about archaeometry, because I don't think that everyone in this room or everyone following this talk is actually familiar with this term. So, what? What is archaeometry, right? Let's start with this. And well, I tried on this next slide to. I took the idea from Facebook. It was very popular a couple of years ago. How society sees someone, how family sees the same person. So I tried to do the same thing for the archaeometry. But before showing you the picture, I would like to just say that archaeometry is actually the application of the methods proper of natural sciences and of the analysis proper of natural sciences to question that comes from archaeology or art history. So let's see how generally society sees the archaeometrist. This. Indiana Jones, right? Because archaeometries, people think we are archaeologists. We are not archaeologists, not exactly, but probably this is the first image that popped in someone's mind when hearing the word archaeometry. And then let's see then how an archaeologist or how a conservator, someone that is actually a little bit more into this kind of work, can see an archaeometrist. Generally, we are this. Because we are the people that can make scientific analysis, that can unveil something about the material. And so generally we are associated, we are linked to NCIS or any kind of possible scientific department, scientific police department. And then finally, we have the scientists, right? Every other scientist that is not in archaeometry, how did he see us? More or less like this. So it's really actually, there is still a lot of debate on the role of archaeometry, if it's a science, if it's not a science. What is archaeometry in general? Well, generally, archaeometry is a very interdisciplinary field that really tries to answer archaeological or art historical questions using, in general, scientific analysis. So now I think I gave you already an idea of what archaeometry is. Now, let's focus on the topic of this talk. As an archaeometry, I study inks. I can study whatever other kind of cultural material, paintings or artifacts, but my work focused on ancient inks. So let's start from here and let's see quickly, before going into the details of my research, how many kinds of ink we know so far, all right? So the first and probably most common kind of ink that we can find, and we can find it from really ancient time, from the beginning of times, it's carbon ink. Carbon ink is based on charcoal or soot that are mixed with a binder, gum arabic generally in the west, and protein glue, animal glue in the east, to obtain an ink that it's indeed very black. It's indeed black as charcoal, right? And then we have planting. Planting maybe is less known. What is planting? Planting can be obtained by simply boiling the tree bark, generally, or any other part of the tree, for some hours in water to obtain sort of a substance which is not exactly black, it's more brownish, but that has the right consistency to be used to write. And of course, generally, also a binder is added to maintain this fluidity and to make the ink stick actually to the support. And then another category of ink is iron gall. Maybe someone already heard about iron gall ink. Generally, it's very much studied because it's very corrosive. So we have any number of documents that show corrosion due to this kind of ink, meaning that the ink arrived to actually eat the support. And now we can even see through completely. So this is generally iron gall ink. It's very acidic. And how can we make iron gall ink? Well, we have to take green vitriol, iron sulfate. This is actually the wall of a cave in which different types of sulfate are growing. And the green one is the iron sulfate. So we need iron sulfate and we need gallnuts. Gallnuts are peculiar kind of nuts that grow on trees. Generally are very popular oak gallnuts, but any kind of tree can have gallnuts. And this happens when an insect lays the eggs inside the tree bark, and as a result, the tree bark expels this nut. These nuts are rich in gallic acid, which is exactly what we need to form a complex with the iron in our iron sulfate to get a pigment, which is called iron gallate, that then is mixed with the binder in a second stage. All right, so iron gall ink is a little bit more complex. It's characterized by the mixture of iron sulfate and gallnut extract to obtain the pigment. And we have actually different types of iron gall ink. We don't have to think that iron gall ink is all the same, because depending on the composition of the metallic salt that was used to make the ink, we can distinguish between different types. So let's say, for example, that the green vitriol that I used was not containing only iron, but also a little bit of copper. Then I will have an iron gall ink that is containing both iron and copper. If the salt that I used was containing also a tiny amount of zinc, then I will have iron gall ink with iron, copper, and zinc. If not, I will have just iron gall ink containing iron. All right, these are maybe 3 ink categories that are still quite well understood so far nowadays. But then we have a 4th category that actually nowadays is posing many challenges to our studies. And it's a category of mixed inks. What are mixed inks? Basically, anything mixing something to create a pigment, and then something else to use as a binder. So we can have iron gall inks that are obtained mixing carbon with iron gall, or iron gall inks that are obtained mixing carbon and just planting, obtained from the bark or even the gallnuts or any other part of the tree. So we can distinguish 2 categories of mixed inks as far as we know. But research is keeping going, so we don't know what we'll find out tomorrow. But so far, we have carbon ink plus iron gall ink and carbon ink plus plant ink. All right, so nowadays, my work focuses mainly on scientific analysis of manuscript. But before, at the very beginning of this research, I had to make a very thorough bibliographic research to try to understand, or at least to try to grasp out all the information we had on different kind of inks, when and where a certain type of ink was used. And so I tried to recalculate all the information to report it all on this slide. I divided, again, you can find here 3 different categories. Mixed things are still apart because so far are still poorly understood, and most of the time we tend not to pay attention that much to this kind of ink just because we still don't have the tools to understand them. So let's consider carbon ink, plant ink, and iron gall ink. First of all, let's have a look at what I call common knowledge. The information that you see in blue is coming from some sort of common knowledge, very popular among scholars and scientists, that unfortunately doesn't have any evidence, at least not yet, but it's anyway very diffuse, so we have to speak about it. So first of all, carbon ink was used everywhere since antiquity. This is common knowledge, but it was also partly confirmed by scientific results, and this is why you can see the second part of the label in green, which corresponds to the scientific evidence we have. Plant ink, well, we have these source telling us that plant ink was the traditional ink in Byzantium. We still don't have any evidence regarding this statement, and also that it was used in Northern Europe between the 6th and 9th century. Still, all this information still need to be confirmed. And then we have iron gall ink. Iron gall ink, for some kind of reason, is believed to be used, well, we know that it's used in the Middle Ages in Europe, but it's very popular to think that from the Middle Ages onward, everywhere in the world, iron gall ink was starting to be used. Let's have a look now at what the treatises tell us. I'm talking about Pliny, Dioscorides. What are all these ancient treatises tell us about the ink? So again, let's start from the carbon. So we have in the Greco-Roman world Vitruvius and Pliny that tell us the recipe to prepare carbon ink, mixing indeed soot and gum arabic or glue as a binder. And also, we have something slightly different. We have Dioscorides that tell us to mix the soot with gum arabic and glue and to add calcanthum. We still don't know exactly what calcanthum is. There is a very big debate. Unfortunately, this is the issue of dealing with such ancient sources. We don't know exactly what they intended to be calcanthum. Definitely is a copper-based substance, right? We can see it from the root of the word. It's copper-based. But what exactly is it? We still don't know. At least we don't know it in ancient time. It becomes clear in the Middle Ages that calcanthum is actually copper sulfate. But for antiquity and late antiquity, we still have no idea. And then, so it's peculiar, however, that Dioscorides say to add calcanthum to carbon ink. This is something very peculiar that, for example, Heraclius, many centuries later, doesn't do, reporting just the recipe as it was found in Pliny and Vitruvius. The reason behind this, probably the antiseptic properties of calcanthum that was extensively used also in medicine because of its antibacterial properties. So the carbon itself, it doesn't deteriorate at all, I would say. But of course, the binder, the gum arabic or the glue, that's organic, that deteriorates, that can be attacked by a microorganism. So adding calcanthum was a way to maintain the ink longer in time and to prevent from molding. Plant ink, well, I came across actually a recipe of plant ink that was always pointed out as a recipe of iron gall ink, but I really don't think it's iron gall ink. It comes from the 5th century, again, Greco-Roman world, is a treatise from Marcianus Capella, and it speaks about gallarum gumeosque commixtio. Maybe some of you speak Latin, however, here we have gallarum, gallness, gumeosque, gum, commixtio, a mixture, that's it. This cannot be iron gall ink. We don't have any iron sulfate, which is what we need to create the complex, the pigment in iron gold ink. So this can't be iron gold ink. This is a recipe, and so far the only one we have of a plant ink. Okay, the treatise regarding iron gold ink, what do we have? First of all, in the 3rd century before Christ, so very early, we have Philo of Byzantium that actually doesn't really give a recipe for iron gold ink, but it's sort of a precursor of it, because it speaks about writing on leather with gallnut extract in water, which is actually brown. So you write on leather with something brown, you won't see it. But then this message, this secret message, was sent to the receiver that was spraying the leather with a mixture of water and calcanthum. And suddenly, you could read the ink. Now, thing is, we said that calcanthum is probably copper-based. But if we assume that by being able to read the ink, Philo intends to make the ink black, then we need to have some iron in our calcanthum. Cannot be only copper-based, because the reaction is not happening with copper. So this is an interesting thing to keep in mind. And then we have any number of iron gold ink recipes in Orient from the 9th century, many different types of iron gold ink with different metallic salt containing iron and not just iron. And then, of course, in Europe, from the Middle Ages onwards, iron gold ink became extremely popular, and we have any number of recipes, as long as book of accounts of one or another cathedral asking please to buy ingredient, buy gallnuts and buy calcanthum and buy green vitriol to make iron gold ink. And finally, the scientific evidence we have so far, what we can actually rely on, because as much as I'm sure that Pliny and Vitruvius were saying the truth, sometimes I still cannot understand what they're talking about. So I have to rely on the scientific evidence. So as I said before, the use of carbon ink in antiquity was confirmed also by scientific analysis. And also, we have found carbon ink on documents from the Middle East between the 7th and 12th century. Plant ink was found in Egypt in the 3rd century before Christ. And curiously, then, in the 9th century before Christ, in Germany and Greece. We still don't know what happened in the middle. What's the connection? How it seems that disappeared in the middle, but it's also true that we still don't have enough analytical data to prove it. And finally, iron gold ink. This kind of ink that everyone thinks appeared just in the Middle Age, from the Middle Ages onwards. Well, no. The first evidence of iron gold ink we have comes from a document. Yes, it's a documentary text from Egypt, written in Greek, coming from Hermopolis, dating at the 1st century. So way, way before the Middle Ages. And then we also have our Mixtapes that unfortunately we're still not able to place in this sort of timeline. So I understand now I gave you a lot of information, and I understand that it may seem, oh, that we know everything on ink, so what's the point of keep studying them, right? Well, if we try, and I swear this was just a naive trial. I didn't try to be scientific in this representation. But if we try to represent all this information I just showed you on a timeline, what we get is this. We have, again, the orange dots for the treatises, the green dots for scientific evidence. I decided to exclude completely from this timeline the common knowledge. So you see that actually we have very sporadic pieces of information all along the timeline. Very sporadic pieces of information. And what we're trying to do with our analysis is just to collect more and more data, trying to fill in the gaps of these very fragmented scenario. And what we want to do is not just to get a timeline, but we would love to be able to create a geochronological map that actually represent what kind of ink was used, when and where. If we had such a map, and when, actually, not if, but when we will have such a map, because it's just a matter of collecting data, when we will have such a map, of course, this could be an incredible tool to help palaeographical, codicological, and textual analysis to place an unknown manuscript in time and space, of course. But unfortunately, we are still not there. I really hope at the end of my PhD, at least to be able to put, let's say, a first cornerstone of this geochronological map, plotting inside all the results that I got in the 3 years of my PhD. Okay, so let's go now more in the details of my project. First of all, given that the idea is to make a big systematic study of all the inks used in Egypt in late antiquity, I am not considering only one collection, but I am considering more than one. So far, I've been working in these 4 places. Yes, it's missing actually, one is missing. So I've been working at the Apostolic Vatican Library on a collection of manuscripts from the monastery of San Macarius, dating at the 9th and 10th century. I've been working at the Egyptian Museum in Turin on a collection of papyrus codices dating at the 7th, 8th century and coming from the library of the Cathedral of Tis. Then I work at the Cambridge University Library on the Mitchelllamas collection, which is a very heterogeneous collection of manuscript coming from the 6th, from a period between the 6th and the 10th century. I was also at the Staatsbibliothek in Berlin studying the manuscript from the White Monastery coming from the 10th, 11th century. And then I was in this beautiful, beautiful, beautiful place at Montserrat Abbey, studying some among the most ancient papyrus fragments that we have. I mean, most ancient considering late antiquity, of course, that date around the 4th century after Christ. So I would like to stress something. When I say that I was working in all these places, I actually mean that I was physically working there. Because every time that we have to analyze a collection, we take all of our scientific instruments and we bring them directly into the collection and we start studying the collection in situ. This, of course, gives us some advantages because generally the institution are quite welcoming, I have to say. It's much better to ask permission to go there than to ask permission to bring a manuscript out of the library, right? So in this sense, of course, it's working pretty well. You can see here, for example, that I was performing analysis in front of a curious community of monks in the Montserrat Abbey this past January. You cannot see the machine I was working with, but you will see it later on in another slide. And so this is a proof that I'm actually working in situ. Every single time I am working directly in the collection. And another peculiar characteristic of our analytical protocol is that we do not take any sample. This would be also an issue, of course, when you're required to take samples out of manuscript. It can be, maybe they are going to give you one sample out of the 100 you asked. Still not enough to perform a systematic study to try to fill in the gaps of this fragmented scenario on the study of inks. So this is another very important feature of our protocol. Unfortunately, though, yes, it comes with a certain disadvantages, because it's true that portable and non-invasive techniques, meaning the techniques that don't require the sampling, don't allow you to go very further in the understanding of the materiality of what you're studying. So this is definitely one of the limits of our protocol that we're trying to deal with right now, and we will see later on how we're dealing with it. Okay, so I'm gonna introduce now our scientific protocol. What do we use to study these things? So we have a two-step analytical protocol. The first step uses the near-infrared reflectography to distinguish the type of ink. And we perform this kind of analysis with this small microscope that you can see up there. It's a small USB microscope that can be just plugged in to your computer. And it's equipped with 3 different lights. We have visible light, near-infrared light, and UV light. What we do is we take pictures of our ink in the visible and in the near-infrared light, and then we compare them. So here you can see that plant ink disappears completely in the region of the near-infrared, the 940 nanometers, while arable ink changes its opacity, but it's still visible. And finally, carbon ink. Carbon ink just stays completely black, and it's very easy to recognize. And this is the first step. We can already distinguish between these 3 types of ink. And of course, it's difficult to predict what's going to happen when we have a mixed ink. This is why they are so challenging to actually properly identify and characterize. The second step of our analytical protocol involves a technique called X-ray fluorescence. What is this? Well, this is a technique using X-rays. You can see here a small picture of the machine. It seems small, but actually it's an 80-kilo machine, a very big one. That generally, anyway, we manage somehow always to bring with us, despite the weight and the dimension. So how does this technique work? Well, here you have the atom, all right, with a nucleus and all the different levels of electron. So an X-ray beam comes, interact with one electron from the inner shell, kicks it out, and then the other electrons that were in outer levels start falling down towards the nucleus with sort of a waterfall effect. In response, the atom emits a characteristic X-ray. What does it mean, characteristic? It means that it's characteristic of the atom. So the iron will emit an X-ray with a certain energy, copper with a different one, so on and so forth. I have my detector here, and I can count how many X-rays of different energy per each channel of energy are coming to my detector. And this is how I can, oh yeah, here you have the same thing, like displayed in a different way. So in the end, what I get out of this analysis is a spectrum with peaks corresponding to each different element. So this is an elemental analysis. Doesn't allow me to see any molecules. What I'm saying, elements, atoms, right? So here you can see actually 2 spectra, one for the ink and one for the papyrus or the support parchment, whatever the support is. This is because the X-ray actually penetrate completely all the layers of my manuscript. Therefore, if I want to see what's in the ink, I have to compare it with the spectrum coming only from the support. So I will take a measurement on an inked area and a measurement on a non-inked area only on the support, and then I will compare them. Here you can see, this is a spectrum of an iron wool ink. You can see that the peak of iron in the ink is way, way, way more intense than the peak of iron in the support. And this is how we characterize iron wool inks. This, for example, is an iron wool ink that contains iron, but also copper. You can see here the small red peak. Yeah, this is, again, our machine. You can see here, you can see it a little bit better. What we do with the results coming out of our X-ray measurements is to calculate for, in case of iron wool inks, the fingerprint. The fingerprint is just the ratio of metals other than iron to iron. And this is characteristic of a certain ink. As we spoke before, not all the metallic salts used to produce iron wool ink were the same. So I can actually, depending on the ratio of elements other than iron in my ink, I can distinguish different types of iron wool inks. All right. Then let's go to the results of the research, the results we've got so far. And I decided to divide the results in two different categories, two different parts. Let's say results that show us what can our protocol do, and results that show us what our protocol still cannot do. Because I firmly believe that we should always keep both of things in mind when if we want to improve and to go further in our research. So let's first talk about the positive news, let's say. What can we actually do? Well, I'm going to present now a series of case studies. Maybe some of you know the manuscript I'm going to present. This is a leaf from a papyrus codex preserved now at the Egyptian Museum in Turin and coming from the library of the Cathedral of Tis. Here in red, you can see the spot where I took the analysis, and here you can see the visible and near-infrared pictures of that spot. You can see actually that the ink is changing its opacity when moving from the visible to the near-infrared region, meaning that we are dealing with an iron ink. Let's see now the results of the elemental analysis that we did with our X-rays. So you have to imagine that every time I'm analyzing my inks, I'm taking a line scan from the papyrus or the support into the ink. This is the intensity of the elements in the ink. We have iron in black, potassium in blue, and manganese in red. You can see that all of them show the same pattern when moving from the papyrus into the ink, suggesting that they were all present inside the ink that we are studying. So the potassium is generally attributed to the binder, while iron and manganese are, of course, part of the metallic salt that was used, of the vitriol that was used to produce this ink. Although something here is curious, because we don't see any copper or any zinc inside this ink. And this made us wonder if actually this ink was produced using something different than vitriol. Because generally in antiquity, they didn't have really, this is coming from the 7th century, I've got to say. In antiquity, they still didn't know how to extract or purify a certain sulfate, in this case, iron sulfate. So normally iron sulfate, green vitriol, always contained some impurity or lower amount of iron metals. It's surprising to observe that on this codex of the 7th century, we cannot see any trace of copper or zinc. So we thought that maybe these inks was actually produced not using vitriol, but using any other source of iron. For example, iron nails or common iron filings. This is a possibility, of course, but also a little bit of a speculation, because unfortunately, we have no way to actually prove this. The only thing it would be to find, for example, an ink recipe coming from the same period and actually stating the use of iron nails or iron filings to prepare ink. However, what's impressive is that the whole collection studied at the Egyptian Museum of manuscript coming from the library of Tis displayed exactly the same features, meaning that it seems indeed it's suggesting that there was a trend in the way of manufacturing inks, that the inks were indeed manufactured all the same way. The second case of study is about a very nice papyrus roll, one of the last papyrus rolls that we actually have, because it's coming from the 4th century, the end of the 4th century, so it's already a very late period to find some rolls. And it's preserved at the Montserrat Abbey, the Rocapuche collection, coming from the area of Panopolis. It's known as the Athanasius roll. So here you can see 3 different spots of analysis, and in all of them, you can appreciate the change in opacity in the ink in the near-infrared region. You can still see the ink. I'm not sure if you can actually appreciated from there. You can still see the ink, but definitely there is a change in opacity, indicating that we are dealing with an ironable ink. Well, in this case, we were very lucky. Sometimes we are lucky. Sometimes people trust us, and they gave us a very small fragment that, of course, they didn't rip off from the manuscript. It was already loose. We brought it to Berlin, and we managed to make an analysis, an elemental mapping of the fragment. Up there, you can see the fragment with the ink. And here you can see the map of iron and a map of copper. For some kind of reason, the labels are missing, but this is the map of iron, this is the map of copper. You can still appreciate the shape of the letter in both cases, showing that this ink was containing both copper and iron. It was an ironable ink of the type that I call 2, containing both iron and copper. Well, the following example, actually, I'm very proud of it because it's a type of ink that is still so far very unknown, not published. We have another record of this same type of ink, but it's just a record we have because a friend of us told us that found the same kind of ink on another manuscript. But it's a kind of ink that I didn't show you at the beginning because it's still unknown. So we didn't know it before starting these research. It was found on a fragment, on a documentary fragment, preserved at the Palaeographic collection in Barcelona. You can see here that there seemed to be no change in opacity between the visible and near infrared. Indeed, there is no change in opacity. But it's weird because the ink, this is a typical feature of carbon ink, and this ink is definitely not black. Maybe you cannot appreciate from the picture, but the color of the ink is actually brown, yellowish, I would say. So it's actually very peculiar ink. And when we perform the elemental analysis, this is what we found. So up there, you can see the intensity of iron. You see that there is not much change between the papyrus and the ink. You cannot see a peak growing or anything. So iron is just not in the ink. What's in the ink? It's copper. Just copper. Could this be connected with calcanton? Probably. But we still don't know. So this is a type of ink containing probably tannin because it's brown. So we think that some kind of vegetal matter was indeed in the ink, and some copper. It comes from the 8th century, I forgot to say. All right. The next example is beautiful. It's beautiful. One of the most satisfying case studies that I had so far. We are dealing with what's called Mitchelllamas Codex, preserved in the Archeometric collection in the Montserrat Abbey. And it's a small papyrus codex, very small, this dimension more or less, that it's divided in 7 different sections, each one containing a different kind of text. We have religious text, we have mythological text, we have 7 different types of text. So we perform, you can see here the picture in the visible and near infrared light. You see that the ink is changing its opacity, so we are dealing with an ironable ink. And here is the fingerprint that I got out of 6 leaves for the first 6 sections, 1 leaf per section. I wanted to see all the different sections to check the ink and to compare them. And here you can see the results. So section 1, the green bar is the content of copper. So you can see that the content of copper in the ink is going up and down, up and down, up and down. It's not homogeneous. This already tells you that this small codex was not written in a single phase, but in more than one writing phase. You can see then that, for example, section 3 and 4 show a very homogeneous fingerprint. Therefore, probably they were written contiguously, but as well as section 5 and 6. But definitely you can see how the fingerprint changes along the sections. And then there was also section 7. And section 7 was actually quite surprising. Section 7 was written with a completely different ink that was carbon-based and not iron wool. You can see here that there is no change in opacity between the visible and the near-infrared micrograph, showing that we're dealing with a carbon ink. The 7th section is actually peculiar because it contains not really a text, but a list of words in Greek that seem to be connected with the practice of stenography. So it's indeed surprising because this was one of the rare times that I found carbon ink on what I thought being a literary manuscript. Very surprising. Because I have to say, it's very rare to find carbon ink in a literary manuscript, but it's very common to find it on documentary manuscripts. You see, these are all documents coming from 5th century, 4th century, in a period in which iron wool was already in use for literary manuscript. We find carbon ink on documentary manuscript. So this poses a question, right? Is it possible that the type of ink was actually connected to the type of manuscript, documentary or literary? Well, I'm going to give you numbers. So far we analyzed more than 170 or 160 codicological units. And codicological units means a unit of a text thought to be all together, thought to belong to the same book or roll or manuscript of any kind. So we analyzed more than 160. And we have something like 77 documentary text and 80 literary text. Out of 77 documentary text, the 86%, meaning 66 of them, were written in carbon. Out of 80 literary manuscripts, 96% were written in iron wool ink. So indeed, it seems there is a trend in the use of the type of ink according to the type of text to be produced. But why? Well, I think this can be explained considering the material qualities of carbon ink and iron wool ink. Carbon ink is a type of ink that just sits on top of the support and can be easily erased just by rubbing it off. So it was really easy to clear the document. Very, very easy. So it was more indicated probably to write ephemeral texts. On the other hand, we have iron wool ink. Iron wool ink, by nature, is extremely difficult to remove because it penetrates inside the support. It's similar to a process of dyeing, for example, a textile. It penetrates inside the support and can be removed only in extreme acidic conditions. So it was not so easy to delete iron wool ink. This is probably why they were using it in text, in manuscript that were supposed to be passed on through generation, that were supposed to form part of a millennial library. All right, so I would like to conclude telling you what we still cannot do, but what we are struggling to find a way to do. Our protocol so far is still not able to detect mixed things. Why? Because with our protocol, I showed you, we can do an elemental analysis, we can see the atoms inside our ink. What I didn't tell you is that we can see only a limited number of atoms, only the heavier one. All the light atoms that generally form part of the organic matter, we cannot see them at all with our protocol. This means that we cannot see organic compounds, unfortunately. This is a very big limit, especially when it comes to mixed inks. Why? Well, because if we have a mixed ink that mixes carbon and a metallic salt, then we are still able at least to see, well, we can see the carbon and also the metallic components in the salt. But if we have a mixed things that mixes carbon and plant ink, well, plant ink is mainly organic matter. We won't be able to see it at all. We will see only carbon ink. And this is a case of a mixed ink we found on a parchment codex much later in time. This comes from the 10th century. It's part of the collection of the Wine Monastery and is preserved at the Staatsbibliothek in Berlin. So you can see that in these two spots, you see actually a change. This is the iron molding, but that spot up there is actually a different kind of ink. That spot up there is carbon ink. But when we did the elemental analysis on that spot, this is what we found. Look at the intensity of iron. It's increasing a lot. So probably this is a mixed ink that was produced mixing carbon and iron molding. This we are still able to characterize, but if this mixing would have contained only carbon and plant ink, there would have been no chance to actually be able to identify it. So, luckily, there is always hope in research, right? Because you think tomorrow is a different day, maybe something's going to change, I'm going to be able to actually find out more about the topic I'm studying. So, the thing is that I went to China last year, and they are like very, very advanced there when it comes to technology. And after exposing this problem in front of a scientific committee, they told me, so you have no reason, no way to study the organic components in your inks. No, unfortunately, I don't have any way because I need a portable and non-invasive tool, and it's very difficult to find one for organic component. Oh, really? Well, you should come and have a look at what we have in our lab. And they show me this. This is actually a new type of mass spectroscopy. Mass spectroscopy is very common in the field of cultural heritage. It was used extensively to characterize organic compounds like dyes, pigments, so on and so forth. Unfortunately, it has always been invasive. So you needed to take a sample, and the sample was going to be completely destroyed. So this was the main limit. However, we have now this new device, which is what you can see up there. It's a new device with a glass wire as a tip. The glass wire can be just wrapped on the ink and then can be put inside this big machine that, of course, is not portable, but as far as the sample holder is portable, we are fine with that. And these can actually determine and identify organic compounds. We did some analysis and tests on mock samples in lab, and indeed we were able to identify gallic acid inside our samples produced using gallnuts. So it was indeed a very nice result. The best part is actually that the amount of sample that you're collecting is invisible. I wouldn't say that this is a non-invasive technique because it's true that there is certain contact between the sample holder and your manuscript, your ink. I would call it micro-invasive. However, the sample collected is non-visible. Therefore, we think that this could be a very versatile technique to apply in this field. And this is what we're trying to do in the future. So to conclude, the first result of this study pointed out that the ink world in late antique Egypt was indeed multivariated. And we are trying to use these differences to actually locate each type of ink on our geochronological maps. And hopefully, with the help of a new technology, we will also be able to take a step further in the characterization of our ink, trying to create a geochronological map which is as complete and accurate as possible. And this is all. Thanks for your attention.
Thank you very much. That was amazing. I usually tweet a lot, but I had to properly pay attention for this one. It's a lot of chemistry and physics,
yeah,
together with the manuscript stuff. I have a few questions for you, but let's open to the audience first. And just to say that we'll read the recording for several of the first questions, and then we'll move on to a more relaxed discussion topic. So if you don't want to be recorded, please.
Those little glass wires that you're using to take the sample, do they come in sort of kits, these little glass wires?
Yes.
Expensive?
So you're asking about the glass wire
Yeah.
as a tip for sampling for this new mass spectroscopy device. Yes, they are like very inexpensive glass. They are common glass wires actually. You can buy them in a stock of 100. You should use a different one for each sample you collect, of course, because this technique is hypersensitive. I'm telling you, the amount of sample collected is invisible, and still the machine is able to actually identify the organic compounds. But yes, they are really, the expensive part is the machine, not actually the glass wire. Yes.
So you literally touch it onto the surface.
Exactly.
Do you scrape it at all?
No, I would say that the kind of gesture you're making could be similar to what a conservator does when performing a dry cleaning. So you're rubbing gently, making sure though that you're not actually scraping off anything, because that would be invasive, a little bit more than just microinvasive. Yeah.
Other questions?
Just a very simple question. You talked about in this presentation some differences you were able to detect between types of ink used across time, across space, across genre even. Did you note any differences across language?
No. Yes. So it's interesting because this was actually my first hypothesis. Of course, I have several languages of manuscript produced more or less in the same areas. Maybe there's going to be a difference. No other relevant correlation as the one that I found between the type of ink and the type of of manuscript was found between language or area or nothing. That was really the most amazing correlation I could find. Yeah.
To Gabby's question,
Yeah.
mine is, does the support material also doesn't matter?
Exactly. This was the other possibility.
Yeah.
Actually, it has been suggested in the past that, and also there is still this idea that Arundel ink appeared with the appearance of parchment as a writing support. This is absolutely wrong. Well, I showed you these example of a beautiful codex from the Library of Peace that was written with Arundel ink, but also the roll of Athanasius was written with Arundel ink. The small codex in Montserrat was written almost exclusively in Arundel ink. So no, there is absolutely no link between the type of support and the type of ink used.
Were there sensible differences in the cost of producing the different kinds of ink? Could that have been a component in the choice? Like, for example, for cheap documents, we'll use a cheaper ink?
Yes, absolutely. I didn't want to go that far in stating this because we still have no evidence. We are trying to look for book of accounts that actually say, all right, so for carbon ink and gamma arabic, we spend so and so, and for unfortunately, I haven't come across any kind of document like this. But it's reasonable to think that carbon ink was the cheaper material because you can actually make carbon out of anything. You just burn it, right? Actually, we have Arabic recipes that were burning date seeds to make carbon.
Nice.
So you can really burn any kind of thing, and you can get carbon. It's a bit more difficult to get the vitriol and the gallnut to actually make Arundel ink. So I would think logically that Arundel ink was more expensive to produce than carbon ink, but we still have no evidence. Yeah.
I have a question about your map.
Yes.
You are going to do this map according to the collections or the provenance of the component?
The provenance.
Because I have, I was expecting to see some names of pathologists or something, but I did not see that. So you will do a geochronological map of the.
I will, in the geochronological map, I will state as a data the place of provenance of a certain manuscript, because it makes sense to think that in a certain place things were made in a certain way. And actually, we were already able to see some clusters because, for example, the manuscript from the library of Tis, of the Cathedral of Tis, preserved at the Egyptian Museum in Turin. I can go back to show you. Yes, here, we saw certain homogeneity inside the same collection. It was all the same type of ink, iron gold ink produced using maybe iron nails, but anyway containing only iron. So what I need to place on my map is definitely the production place of these manuscripts.
Do you know where?
From the library of Tis. Tis is from Egypt. They are all Egyptian inks, and this is a collection coming from the Cathedral of Tis, which is a city next to Soham.
It's called
Tis or Tis, yes.
The green vitriol.
Yes.
Is this very commonly found, the sources of it, or do you know where these sources are?
Yeah. So, of course, it would be amazing. What we're trying to do, what we've been trying to do, unfortunately, so far with no results, is to try to get a map of ancient mines containing iron gold ink and possibly stating also, iron gold ink, vitriol, and possibly stating also what kind of vitriol could be extracted from the mine. We found no such a source so far. However, sulfates, in general, vitriol is sulfate, right? Can be green vitriol, iron sulfate, blue vitriol, copper sulfate, and we have all the means to think that in antiquity it was actually a little bit a mixture of different sulfate because it was never purified. So, of course, it will be amazing to be able to link a certain type of vitriol with a certain mine in a certain place, but so far it's not possible to do. However, sulfates are very common, so I wouldn't say, oh, in Egypt sulfates were coming only from here and there. I think they were pretty diffused.
Any information on those shopping lists as to where they were getting the stuff from?
No, and unfortunately, I didn't find any shopping list or any book of account, unfortunately. I mean, if you ever come across of anything like that, please let me know, because it would be a very valuable source of information. Yeah.
Do you think there was any attempt to produce different colors just for aesthetic reasons? Mixing different ingredients?
So when we deal with later manuscript, we can also find different pigments, different colors, and also in like pharaonic documents you can find many different colors. But generally, the color of the text was black. And I would say that I have, for example, cases of documents that were written in red, but it was red. It was like it was really minium or cinnabar, a different kind of pigment. So I would say that when you see carbon or iron or copper or stuff like that, they were trying, the intention was to get something black. Yes, because they had all the means to get something red, blue, or in a different ways, in different materials. Yeah, so I would exclude it.
They would do that mostly for decoration.
Yes.
And text.
Yes.
No.
I mean, yes, of course, it was used mainly for decoration. I have a couple of cases of documents written in red ink that we don't know, but they are really like two. So anything could have happened. Oh, I don't have any black ink anymore. Yeah.
Speaking of colors, are you going to do a comparison with textiles? Because in antiquity we have these colorful things, and the production of, purple, I think, was a monopoly or something like
Yeah.
that. So,
Writing on leather as well.
yeah. So also, yeah. So are you going to?
Well, not so far. We're not planning to do such a thing. Although it would be interesting to do after we get this new machine that I was telling you about, because actually the dyes used in textile are almost always organic based. Like also the purple dye or the saffron or the indigo, they were all organic based, meaning that with our current protocol, we can see nothing there. So this is why we never planned to do such a thing. But with this new machine, actually, this machine has been actually in China, that we're using it to analyze dyes on silk. So it could be, I think it has a great potential in the study of dyes on textiles. Yes, so maybe for the future. For a postdoc, maybe.
Yeah.
I think for a postdoc, I will have enough to try to understand exactly how to get the most out of it.
We spoke about this already. I would like to talk to you about what technology could you use to do your math.
Exactly.
And I have a couple of ideas, but maybe after we stop.
Yes.
Does anybody else want to be recorded, or shall we stop?
Yeah.
Okay. Oh, we can continue talking then.
Yes.
Just stopping the broadcast. Yes.
Stopping the broadcast. I'll fiddle with this.